Hello and welcome to this video on matrix systems in 3x3. There are 5 possible systems for 3 planes and we need to be able to distinguish between them. So the 5 possible systems are: firstly, the planes meet at a single point; secondly, that 2 or more of the planes are parallel to each other; thirdly, that the planes form a sheaf, so rather than meeting at a single point they share a common line; fourthly, a prism, where the 3 planes intersect in pairs; and finally, where they're all the same plane. We're going to start by considering consistent equations and inconsistent equations. A system of equations is consistent if there's one or more solutions that satisfy all of them, and a system of equations is inconsistent if there are no solutions that satisfy all of them. Let's consider 2 dimensions firstly, because you're used to them. So are these the same line, 6x minus 10y equals 14 and 9x minus 15y equals 21? Well, yes, they are both the same line. They're both equivalent to 3x minus 5y equals 7, which you can get by dividing the first one by 2 and the second one by 3. And what about these 2 lines? 2x plus y equals 10 and 4x plus 2y is equal to 23. Well, they're not the same line. If you double the first one, you get 4x plus 2y equals 20. So they're equal to different things, but they are parallel. They've got the same gradient, but they can have different y-intercepts. And so we can extend this idea to planes. So are these the same planes? 3x plus 7y plus z equals 8 and 6x plus 14y plus 2z equals 16. Are they the same plane? Well, yes, they are the same plane. If you double the first one, you get the second one. And they are consistent and they have an infinite number of solutions for x, y and z. And what about these 2 planes where the 16 has been turned into a 17? Well, no, they're not. Okay, they're not the same plane. If you double the first one, you still get your 16, but they are parallel planes. They're inconsistent, they have no solutions in common because they're parallel. So how might we demonstrate consistency for 3 planes? Are these 3 planes consistent? So to find out whether they're consistent or inconsistent, what I've done is to manipulate them to get 2 equations in terms of 2 variables, in this case y and z, and compare them. So if I do equation 1, take away equation 3, I get 3y minus 2z is equal to 5. And if I double equation 1 and take away equation 2, I get 3y minus 2z is equal to 8, and these are obviously inconsistent. So this slide shows you how consistency and inconsistency relates to our 5 possible systems. So for consistent systems, the planes can meet at a single point. We can have a sheaf, or they can all be the same plane, because in each case, all our planes are meeting. Whereas if they're inconsistent, we've either got a prism or 2 or more planes are parallel, because there are no solutions for all 3 equations. I've created a flowchart for us to work out each of the 5 possible situations. So we start by finding the determinant. If the determinant is non-zero, then that means the planes meet at a single point. But if the determinant is 0, it can still be any of the other 4 possibilities. So if we get a 0 determinant, the next question is, are the equations consistent? If they are, then all we need to decide is if the planes are the same. If they are the same, then it's all the planes are the same. And if they're not all the same, then we've got a sheaf. Whereas if the equations are inconsistent, then we just need to check if any planes are parallel. If 2 or more are parallel, then 2 or more parallel. And if none of the planes are parallel, then we have a prism. Here are 6 sets of equations, A to F, and I would like you to use my flowchart to decide what each set of equations represents. Answers available on a separate PowerPoint. Thank you for listening.